Hi, a little while ago I picked up what was probably one of the best eBay scores I've had for an awfully long time. This is a Kodak Motion Corder motion analyzer. What it's basically, it's a very high-speed video camera system. There's a remote camera head here, and this will actually record up to 10,000 frames a second video, although 10,000 frames a second resolution is actually pretty low, but it will do, for example, 240 by 256 at 1,000 frames a second. When it was new, this was maybe sort of 12,000 quid, something like that. There's actually one on eBay at the moment on a buy it now for about 4,800, and I got this. Clearly the guy didn't know what it was. Buy it now, 50 quid. Thank you very much. This is actually manufactured by a company called Photron, who specialise in high-speed cameras. Kodak produced some of the first high-speed video systems quite a long time ago, originally a tape-based one, which you can see some info on my website. But their high-speed camera division got taken over and merged, and there's quite a lot of sort of history. So the later models are actually badged, manufactured by other companies. Thanks very much to Russell at Photron UK. I actually got the software that lets me download images from this, so I can actually get images through. There's a SCSI port on the back, and I can actually download the images from it. Let's take a quick look around this unit. Got the user interfaces, just a set of buttons here. The feedback through a monitor, there's a video monitor, there's also an optional viewfinder that can go on here that I don't have, but I'll probably get a little TFT screen or something to stick on the back of there. Got these main connections here. We've got video out, that's the user interface. Sync out, that is a signal which corresponds to the camera's frame sync, so that if you say running 1,000 frames a second you get a 1 kHz signal out of there, and that would typically be used for things like strobes. If you need a lot of light, then you might want to use a high-speed strobe. It's also used for syncing up multiple cameras. If you've got several of these cameras, for example, shooting different angles, you might want to keep them all in sync, and that's what that's for. That's got an external in, so that'll be to synchronise from other units, or possibly to, if you've got a strobe that you can't control, you might want to actually sync the camera to the strobe or to some mechanism. Trigger in, that's an opto isolated input that just takes a signal of a TTL level signal. Trigger switch in, that's just a contact closure, so you can trigger it from a contact. RS232, just general control interface. Mains in down here. What this thing here is a link. Basically this power supply is actually a separate unit on the bottom that you can actually slide off, so you could run it from a separate 12 volt supply. If I take this link off, you could actually run this off 12 volt DC, which might be useful if you're using it on some sort of mobile application, and this is just a link to link the power supply into the main unit. And around the other side we've got camera connection, big multi-pin connector, so multi-way connector there. Video and DC out, that's for the viewfinder. MCDL, that's multi-channel data link. That allows you to feed data into the system that's then recorded alongside the video data. So you might be looking at some sort of system, say maybe a mechanical system, and you could perhaps feed the input from maybe a displacement sensor or some other sort of sensing device to actually, so you could actually look at the video as well as other parameters. And there's a SCSI interface, that's for downloading images into a computer. Power connection. The other thing in this power supply, there's actually an electronic transformer for running halogen lamps, so I think you can run about 100 watts worth of halogen lamps off this connector here, so that's just really convenient. So you've got the power and lighting together here, because one thing you do need with high-speed cameras is a lot of light, and I've actually seen some pictures of like a little lighting rig that actually clips onto this camera head to provide a sort of complete unit. These are commonly used for things like looking at industrial machinery. So for example, if you've got some big production line running at some very high speed, this is a quite common tool to actually figure out, for example, if it's jamming or something's going wrong. This is the actual camera head. It's on about 5 meters of cable, so it's sort of quite easy to locate. It's actually got tripod mounts on all 4 sides, very solid feeling, rugged assembly. It's a standard C-mount CCTV lens. You actually see the centre in there. As a comparison, this is the head from an earlier generation version, one that I reverse engineered a few years ago, so you can see the camera performance is actually fairly similar. This is actually high resolution, but the frame rates are similar, so you can see there's rather a lot more to this thing. Most of this is board packed full of through-hole electronics. Just a quick look inside this old camera head just to show how much stuff there was. There's the front unit there with the actual CCD on it, and then this incredible big chunky connector on it, and then these are probably about the most packed through-hole boards I've ever seen. They're just completely solid components. All these are doing, these are all just basically analog amplifiers and buffers. The output from this particular cam was 16 parallel differential analog signals, so these are all just amplifiers and differential drivers. There's another 2 boards which handled the all the timing here, again all through hole, all very old school. We've got some of these variable delay lines here for tweaking the timing, HCMOS, LS, TTL. And so this takes a standard C-mount camera lens, so you might use something like this, but for high speed you need a lot of light, so you might actually want to use something that's got quite a decent sort of big aperture. So let's just stick this lens on like this perhaps. This thing's got a very simple user interface. There's just a row of buttons on here. There's some sockets for things like external triggers, and the output comes via composite video. Obviously originally it sort of come with a CRT monitor, but I just got this cheapo sort of 25 quid car monitor from eBay. Does the job fine, just using it as a monochrome composite video monitor. And so the user interface is really simple. You've got live mode, which is just showing real-time images from the camera. You then, there's a simple menu system that selects various things like trigger mode. That lets you do a pre or post trigger, a bit like on a scope, so you can either trigger it and it'll start recording for a certain amount of time. The record time's quite small. On say 1,000 frames a second you only get about 2.5 seconds. That's recording obviously into internal dynamic memory. Smaller frame times you get longer recording, and at the highest rates the record time stays about 2.5 seconds, but the frame size reduces. Sensor is, again, it will basically continuously records into RAM until it sees a trigger signal, then it records another half the memory, so you end up with the event centered in the memory plus whatever happened before and after it. There's also random mode where you can tell it to record a certain number of frames on every trigger, so if you've got an intermittent event you can make it record say 100 frames every time that trigger occurs until it fills the memory up. And frame size selection, say up to 10,000 frames a second. Obviously it does lower frame rates, which in the menu for that is really for setting up. Yeah, 30-60 frames a second you might as well use an ordinary video camera, but these are quite handy for setup. The big difference you see as you go up in frame rate is you need a lot more light, so as we're now down to 125, this isn't a particularly well lit subject, but as soon as you start getting to 1,000 frames a second you start needing quite serious amounts of light, because you're talking 1,000th of a second shutter time. The display size, you can reduce the display size just to increase memory. For those modes that have got higher frame size, you can actually reduce that to give you a bit more record time. Gamma correction, that just controls the curve between the brightness and the pixel values. The recording process is really simple. The normal mode is live, which is live camera display. You just hit record ready, that's basically arms. It's now just sitting waiting for a trigger. As soon as it gets a trigger it starts recording, and then goes back to live mode when it's filled the memory up. So that's now all recorded. I can just hit play, and I can now then play that back at various different speeds. I can slow that down, I can go forward, reverse. So it's really simple, and then obviously I can select frames to download. You can also set up how much of that display appears on playback, because earlier systems they'd typically be used with say a small VCR or something to provide output on videotape, if you weren't using the SCSI interface. Right, so we've got the covers off. Let's take a quick look around. This is the user front panel with buttons on it, BNC connectors, and the RS-232 port and BNCs on that side. Nothing particularly exciting there. And on this side we've got the SCSI connection camera interface. The camera connectors, a load of coax connectors, the 2 here and then 4, so these will probably be the drive signals out and these will be the analog signals back in. One thing I noticed, the boards, they're not only sort of retained by this cage, they're actually screwed in. Each board was actually individually screwed to this bracket, so they were really held very very solidly. So it looks like we've got 3 boards in here plugged into a back plane. I'm guessing the other sockets are probably for memory expansion, because there are a couple of memory expansion options on this thing. Right, so this first board is clearly the front end. We've got the camera connections here. Bit of bodgery going on here. These things, they look like pots. I think they're actually adjustable delay lines. They're all sort of glued down. I'm guessing that's for sort of fine-tuning of the timing signals. They maybe didn't get quite right and found they had to do some tweaking on them. If you go down here, this is the signal from the camera, and these are sampling 125 megahertz sample and hold amplifiers. So it looks like there's 2 analog channels, so there's probably 2 parallel channels coming out of the camera, and there's these sample and hold amplifiers. We've got a whole load of analog stuff. This will be anti-alias filtering and various other analog stuff. And then there's a couple of A to D converters. These are 10-bit 60 megasample per second A to D converters, and these go into this big FPGA. There's an EEPROM here, that will be the configuration data for the FPGA. There's crystal for the time base. There's some RAM up here. There's some configuration switches. These memories are actually designed as video memories. I'm guessing they're probably being used as a FIFO here, because obviously there's not enough memory for it to hold the entire storage thing. But these have actually got, in their day, quite high speed sort of serial interface, so you can shift a whole load of data in quickly serially and then transfer it a row at a time into the memory array. They were for a short time used on video cards and similar things like that, where you needed a fairly high data rate in one direction. I actually used something similar in a design I did a long time ago for a video frame grabber as well. Right, this is the second board. Again, we've got some of this frame memory here, another FPGA, not a lot else. It looks like this is the output to the BNC, so this is probably going to be the video output circuitry for generating the on-screen display and everything. And that's probably about it actually. There's not really much else on here. It's called POENC, I'm guessing encoder perhaps. Some more little bodges over here. Right, this board looks like where a lot of the action's going on. We've got 2 great big FPGAs in the middle of it. There's the SCSI interface down here. It's going into, I'm guessing that's a Fujitsu SCSI interface chip. And up here we've got some flash memory. I'm wondering that's maybe the FPGA configuration in there, perhaps. Some more memory of some sort there. There's a couple of ROMs and there's an NEC processor there. It's a V50 series. I think it's a 16-bit NEC processor. So that's going to be all the main software in there. It's a backup battery. It's a fairly chunky backup battery. That's probably backing up that. There's maybe some SRAM down there. And the other side there's this subboard that's got all the DRAM on it. There's DRAM chips on both sides of this PCB. There's a SRAM chip on the back as well, and a few other odd bits and pieces. Right, underneath the back plane we've got the power board, which initially looks like there's actually nothing happening, but if you see these pins here, it's actually a big stack of DC to DC converters. There's a variety of different supplies, 5 volts at 4 amps, so that's plus minus 12 volts at an amp, another plus minus 12 volts, so that more 12 volts. Is probably some of these are pretty analog supplies for the camera, and one massive great big one, that's 3.3 volts, so that's going to be for all the logic. And interestingly, this one's heat sinked to the main outer, where these other ones are actually heat sinked to the inner plate, which probably isn't doing much in terms of conducting heat because it's steel, not aluminium, so you're not going to get a great deal of heat conduction from here up to here. So these other ones probably aren't very heavily loaded, but this one's clearly the big one that's supplying most of the power to all the FPGAs and all the DRAM. If you see a spec on that, but that's going to be a good sort of maybe 10-20 amps or something, I would imagine. a few other bits and pieces around the edge. There's a fuse, there's a filter below it, some adjustments. These are for trimming, fine trimming the voltage. One little detail I noticed that's actually not uncommon on boards. There's a jumper link to allow this connection to be connected to the 0 volt line. All of them have got it. The reason for that is for EMC performance, usually for radiated emissions. It can be very hard to predict whether you get better performance by connecting ground to the chassis or not, and in some cases connecting it at different places gives different results because of various sort of standing waves and things like board inductance. So it's actually not that uncommon to see option links, so they don't have to redesign the board if they don't really know what's going to give the best EMC performance. It's not uncommon to have these option links so that they can link it or unlink it just while they're doing testing to find out which gives them the best performance. And also on the backplane board, it's also got these links, and in fact you can actually see two of them have actually been linked over. So there and there, that's where they found they obviously got the best performance by linking it on the backplane there. Some pretty serious construction all round. We've got this great big thick chunky aluminium casting here. We've got some soft EMC sealing stuff in here, and so the whole case is made out of a custom extrusion, aluminium extrusion. And even the nameplate, there's this nameplate on the side. This is actually a piece of aluminium that's locked in with this little Allen screw. So that's actually a completely separate piece of sort of very nicely painted aluminium with the nameplate on it. So very much built up to a spec and not down to a budget these days. It was actually screwed together so hard that I actually snapped an Allen key in the process of taking it apart, which doesn't happen very often for an Allen key that size. Right, just taking the front off. This is just the front sensor assembly, little PCB and the flex cable down to some more boards in the back. You see this is a nice custom extrusion. The tripod mounts all slide into here. Very solid, rugged piece of kit. There's also a rubber gasket on the front to keep it waterproof. Interesting arrangement of stacked PCBs in here. Some copper heat sinks, obviously to conduct heat to the outer casing. Interesting they chose to stack the boards this way rather than that way. I would have thought it would be more, you get more packing density by doing them lengthwise, but I'm sure they had their reasons. There's some ferrite rings on here, RF suppressions, 2 coax connections from the camera head. I'm guessing that's the video data out, and all this lot is probably going to be the drivers. CCDs have got quite high capacitance, so when you're driving them at high clock rate, sort of several megahertz, you need quite a lot of current to drive them. I've just taken the top edge of the board, and you can see this is actually a Texas Instruments CCD driver. And it looks like the way they've tracked it, they're probably using multiple channels in parallel, because it's interesting, looks like there's actually 4 drivers there. I'm guessing maybe they're using some of them in parallel to increase the current, so obviously this CCD is probably going to be clocked faster than conventional ones. There's also something in the manual about if you run it over 1000 frames a second, there's actually a timeout to avoid the head overheating, because obviously the clock rate, the increased clock rate is going to cause more driver dissipation, driving high frequency signals into the capacitive CCD. I'm not going to bother stripping the rest of these down, they all look fairly similar. There's a lot of these purple, these are Sanyo Oscon capacitors, which are very low impedance, solid dielectric capacitors. And again, that's so they can provide a high instantaneous current to charge the capacitance of the CCD. And here's the actual sensor. So this is going to be clearly a highly special custom-made sensor. You can see it's actually in a socket. There's actually some little socket contacts in the PCB, and you can see there's a mask over it. Quite often what these CCDs have is they have a sensing array and a transfer array, so that when it takes the image, it shifts the data into a second array, it then shifts it out for actually reading the data. But apart from that, there's not really anything else on this board. It's just a few capacitors and the sensor itself. This is inside the power supply base. Nothing at all unexpected. You've got a bog standard switch mode power supply by TDK, filtered AC inlet, and there's also a second filter here. The only other thing in here, there's a halogen lighting transformer. It's an electronic lighting transformer which is all potted, so there's nothing to see. It's just a bog standard lighting product that provides the supply for the light socket on the back. Right, I had to take this apart. I couldn't get this light output to work. It's got one of these electronic halogen transformers in it, which appears to be dead. Maybe that's why the unit was junked. The light stopped working. Don't know. Strip the plastic of this transformer, but the whole thing's potted in this butter coloured stuff, so I really can't be bothered to crack that off. These things are so cheap. I'll just stick a new one in. I've made up this simple lighting rig. This is just a couple of dichroic halogen lamps on some microphone goosenecks, which gives a fairly flexible way of supporting light and sort of attaching it to the camera for convenience. These do get rather hot. These are 20s, but they'll also run 50-watt ones, which get really hot, but they give enough lighting to do 1000 frames a second at fairly close quarters. And this is quite a nice macro camera lens, which is really good for doing close-up stuff. Standard CCTV fitting macro lens. I can't remember how much I paid for that. It was quite a long time ago.